In lessons 2 and 3 of abstract algebra, starting with the concept of set, I explained algebraic structures with one and two binary operations respectively. The structures with one operation are the semigroup, the monoid, and the group. The semigroup is a set endowed with an operation which is associative. The monoid is a set endowed with an operation which is associative and has a neutral element. The group is a set endowed with an operation which is associative. It has a neutral element, and every element has an inverse element. To each of these structures, we add the adjective abelian to its name if, in addition, the operation is commutative. The structures with two operations are the ring with identity, the commutative ring with identity, the integral domain, the field, and the division ring. Among the two operations in the structures, we think of the first as additive and the second as multiplicative. For the ring, the additive operation defines an abelian group and the multiplicative operation a semigroup. If the multiplicative operation is commutative, then the ring is commutative. If the multiplicative operation has an identity element, then the ring is a ring with identity. Elements that are not equal to the neutral element E of the additive operation we call non-zero. In general, in a ring, we can multiply non-zero elements, and the result can be the neutral element E. Such elements are called proper zero dividers. If a ring does not have zero dividers, we call it an integral domain. And if, in an integral domain, all elements except the neutral element E have multiplicative inverses, we call it a field. If all properties of a field are valid except commutativity of the multiplicative operation, then the structure is called division ring. In all structures with two operations, the additive and multiplicative operations are linked through the distributive property. You can review lessons 2 and 3 if the previous summary was too brief. In this video, I will discuss more complex algebraic structures resulting from pairing two of the structures mentioned above. Let's start. One of the structures to be paired is chosen to be a ring. The set of the ring will be indicated by K and the operations by dot plus and dot times. It is customary to call K the scalar ring and its element scalars. Be careful. You are used to work with the traditional vectors, which are multiplied by real numbers. You call the real numbers the scalars, and your brain may have developed the false impression that scalars are only the real numbers. You need to remove this misconception from your brain. The ring can be any set beyond the real numbers as long as the ring conditions are obeyed. Hence, a scalar may be any object that traditionally you would not think is such. The second structure that is needed for the pair can be selected to be any of the algebraic structures that we have defined. The minimal structure is a semigroup. However, looking at the most popular applications for guidance, it is more useful not to start at the lowest level and instead require our second structure to be an abelian group. Let's indicate the set by V and the operation by O+. We think of the O+ operation as an additive one. The elements of V are now to be called vectors. You can imagine the elements of V as oriented segments similarly to the traditional vectors. However, this is only a graphical representation to help your intuition. The real meaning of the vectors results from the definition of the algebraic structure. I will indicate vectors by a bold-faced letter. As things stand now, the two structures are unrelated. To link them, we will need a binary operation that takes a scalar and a vector and maps the pair to some object. To create an interesting structure, the image must be a vector. Loosely speaking, the scalars multiply the vectors to scale them up or down. Since the O dot operation links elements of different sets, we classify it as an external operation on V compared to the O+ operation, which we classify as internal. We often use the term scalar multiplication when we refer to the O dot operation. The scalar multiplication is not completely arbitrary. To it, we impose a few conditions, known as compatibility equations, which are motivated by our experience with vectors in Rn. These are: 1. The scaled sum of vectors is equal to the sum of the scaled vectors. 2. Scaling a vector by a scalar, which is a sum of scalars, is equal to the sum of the scaled vectors produced by each scalar. 3. Scaling a vector by a product of scalars is equal to the vectors scaled successively by each scalar. We can interpret the conditions 1 and 2 as distributive properties of the scalar multiplication relative to the two additive operations. And we can interpret condition 3 as mixed associativity for the combination of the ring multiplication with the scalar multiplication. The structure resulting from the pairing of the abelian group V, O+, and the ring, as described above, is called a module over K. If the ring is a ring with identity, we add an additional compatibility condition. Scaling any vector by the multiplicative identity element leaves the vector unchanged. In this case, we call the resulting structure a unitary module over K. If the ring is a division ring and the four conditions are imposed, we call the resulting structure a vector space over K. Notice that, for a vector space, the multiplicative operation of K does not need to be commutative. However, in applications, often K is a field. Let's return to the unitary module V over K. We add to the set V a multiplicative operation O times, such that it becomes a ring. Furthermore, we add another compatibility condition for the new multiplicative operation. Scaling a product of vectors is the same with scaling either vector and then multiply the result with the other vector. As previously, we can interpret the condition as a mixed associativity-commutativity for the combination of the O dot and O times operations. The resulting structure from the pairing of the two rings as described is called an algebra over K. If with the second operation the vector space becomes a division ring and not just a ring, then we call the resulting structure a division algebra. In Lesson 3, I have commented that some mathematicians drop the associativity of the multiplicative operation in the ring to allow for non-associative rings. Similarly, we can talk about non-associative algebras. I will leave non-associative algebras as a topic for a future video. If this is your first time you're learning about algebraic structures, you are probably lost with all names and find hard to remember what properties are implied for each of them. Do not worry. As you study more abstract algebra, everything will become natural. The most important structures repeat themselves. Groups, fields, vector spaces, and algebras eclipse the rest structures, especially if you study natural sciences. Furthermore, when you encounter vector spaces and algebras, they're usually built over a handful of fields. In most of the cases, these are the fields of the rational numbers, the real numbers, and the complex numbers, although I have not discussed anything about complex numbers. And sometimes, the ZP field is used. Therefore, at the beginning, you should focus to understand these structures. In Lesson 1, I used the real numbers as a motivation for introducing abstract algebra. There, I claimed that the set of real numbers endowed with the operations of addition and multiplication is an algebra, but the simplicity of the set obscures the algebra. Now, I am in a place that I can make the previous statement precise. The set of the real numbers with addition is a vector space over the field of the real numbers with the scalar multiplication coinciding with number multiplication. Then, in a vector space, the multiplication of numbers is added as the second operation, and an algebra is created over the field of the real numbers. In this structure, the real numbers are, at the same time, scalars and vectors. The multiplication between numbers is simultaneously an operation between scalars, an operation between vectors, and scalar multiplication. And the addition of numbers is simultaneously an operation between scalars and an operation between vectors. There's an alternative way to see the set of real numbers as an algebra. This way is based on the fact that the set of rational numbers is a subfield of the real numbers. Then we think of the real numbers as an algebra over the field of the rational numbers. In this case, the real numbers are the vectors, and the rational numbers are the scalars. In fact, anytime we have a subfield K of a field F, we can claim that F is an algebra over the field K. The elements of F are the vectors, and the elements of K are the scalars. Let's discuss a more interesting example of an algebra. An m by n matrix is a rectangular arrangement of objects placed in m rows and n columns. Symbolically, We indicate a matrix by a boldface letter or by enclosing the entire arrangement of the objects inside square brackets, as shown on screen. We call the objects of a matrix the elements of the matrix. To represent the elements of a matrix collectively, we use two indices, one for the rows and one for the columns. For example, the symbol x2, 3 stands for the element at the intersection of the second row with the third column. Instead of showing all elements of the matrix between square brackets, a shorthand notation is to enclose the general element in square brackets. There's an alternative point of view of matrices which proves very useful in many situations. Each column of the matrix may be seen as a vector in Rm. Hence, a matrix is an ordered horizontal collection of n vectors. Similarly, a matrix may be seen as an ordered vertical collection of m vectors in Rn. Consider the set of all m by n matrices with real elements. Symbolically, we indicate this set as follows. Usually, we drop the R from the notation. In this set, we define the addition of two matrices X and Y to be a matrix Z whose elements are the addition of the corresponding elements of the two matrices X and Y. Notice that we have abused the notation by using the standard plus sign to indicate the matrix addition. It is easy to see that MMN, equipped with the addition of matrices, is an abelian group. The neutral element is a matrix whose elements are all zeros, and we call it the zero matrix. For each matrix X, the matrix whose elements are the opposite elements of the elements of X is the inverse with respect to addition. It is indicated by -X and called the opposite matrix. We would like now to introduce a multiplicative operation in MMN. Obviously, we can define the multiplication of two matrices X and Y to be a matrix Z whose elements are the multiplication of the corresponding elements of the two matrices X and Y. However, it turns out that such an operation is not useful. If both operations, matrix addition and matrix multiplication, are defined this simply, then we have not created anything new. We are still adding and multiplying real numbers the standard way. To get something new, the multiplication of matrices must be more complicated. It turns out that a useful definition can be given only for square matrices, that is, for matrices with equal number of rows and columns. The number n equals m will be called the dimension of the matrices. The set of n-dimensional square matrices is simply indicated by mn. In this set, we define the Cayley multiplication of two matrices, which produces a new matrix whose elements are the product of the rows of the first matrix with the columns of the second matrix. This definition is not as strange as it might appear at first encounter. For the viewers who are familiar with dot products of vectors, if the first matrix is interpreted as a collection of horizontal vectors and the second matrix as a collection of vertical vectors, then the Cayley product of the two matrices has as elements all dot products between the two sets of vectors. The Cayley multiplication is an associative operation. This can be verified easily by computing the elements of the final matrix in the two possible calculations. The Cayley multiplication is not a commutative operation. This can be verified by multiplying two simple 3 by 3 matrices. There is an identity matrix. This is the square matrix that has units for all diagonal elements and 0 for the rest elements. To study inverse elements, the calculations with matrices are more effort requiring. For this reason, beyond this point, I will focus on 2 by 2 square matrices, and I will present square matrices of any dimension in a future video. Given a two-dimensional matrix, we define two quantities associated with it. First, its determinant, which is a number. Then it's a joint matrix. Next, we observe the relations. From these equations, the inverse of a matrix can be defined if the determinant of the matrix does not vanish. A matrix for which its determinant does not vanish is called non-singular or invertible. If X is an invertible matrix, then its inverse matrix is. From the previous discussion, it follows that the set of all two-dimensional square matrices endowed with the Cayley multiplication is not a group. However, if we confine ourselves to the subset of invertible matrices, then it is a non-commutative group. Now, looking at the set of two-dimensional square matrices endowed with the operations of matrix addition and Cayley multiplication, we see that it is a ring with identity. However, it is not a field since not all non-zero matrices have multiplicative inverses. You may ask, what about if we confine ourselves to the subset of the invertible matrices? Unfortunately, this fails to create a field too, since the operation of matrix addition is not closed anymore. For example, the invertible matrices G and I shown on screen add to a non-invertible matrix. Now, we introduce the field of the real numbers, and we allow matrices to be multiplied by real numbers. That is, we introduce a scalar multiplication. Once more, we abuse the notation, and we indicate the scalar multiplication with the same symbol used for the multiplication of numbers. It is easy to verify that the scalar multiplication, the operations of addition and multiplication of real numbers, and the matrix addition and multiplication satisfy the 5 compatibility conditions, and hence an algebra has been created. And by concluding this example, I have finished my presentation. I hope you liked it. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.